So thanks, Rob, for that introduction. I'm going to take one from Dean's playbook and say that this isn't my presentation, so any questions can be referred to Alejandro, who thinks that being in the Galapagos for a conference is more important than being here. So with that being said, I'm going to deliver you this talk, Edible Synchrotron Science, Meat, Cheese, and Chocolate. So I'm just going to go over kind of briefly meat and cheese, a couple of things that we do in our research lab at the University of Guelph, and a little bit of my research into chocolate. So I want to go over a little bit about greenhouse gas emissions. So agriculture and food account for about 26% of worldwide what we call equivalent CO2 emissions. So that also is including like things like methane and the equivalent like heating capacity of that. And we can break that down and look at the majority of it is actually from livestock, crop production, and land use. And we can dig into that a little bit more. So what we eat really matters. So specifically with beef and dairy, they're some of the largest contributors to greenhouse gas emissions. So if we kind of look at beef itself, 1 kilogram of beef produces the equivalent of about 60 kilograms of CO2. Same thing with cheese. You have about 21 kilograms of CO2 production for every kilogram of cheese that is produced. So this requires a large amount of land and leads to a lot of deforestation and changes in soil composition. And with specifically in the dairy industry, large methane production. And methane is actually significantly worse at warming than CO2 is. So what if we switch to plant-based materials? So there's essentially an environmental push because the production per gram of protein from beef and lamb and things like that are significantly higher than plant-based alternatives such as wheat, corn, soy, and things like that. So I'm going to kind of go over two ways that we can kind of tackle this by looking at plant-based ingredients to replace basically dairy and cattle. So first will be a plant-based alternative that we've developed in the lab, and then the second will be basically a cheese alternative. The commercial meat analogs that are on the market right now are typically burgers, sausages, and nuggets. So they're all kind of ground products. We like to compare these to concrete. So essentially, a concrete's a composite material. You have fine and coarse aggregates, and it's bonded with a fluid or cement. So we like to compare like the meat analogs to this. We essentially have small and large chunks of extruded vegetable proteins, and then it's bonded together with essentially starch and gums. On the market, there's quite a limit on whole analog muscle analogs. So that's what we wanted to focus on. So there are a couple of whole muscle analogs on the market currently, but they all use extrusion or shear cell processing. So these all use high temperature, high pressure, and shear, and this changes the overall protein structure, and which also in return changes the function of these proteins. There's also large startup costs and research costs into developing these. As mentioned before, there's extensive processing of these proteins. So you're denaturing them, we don't really know how they're functioning before versus after. And lots of these don't really simulate actual raw meat products very well. They're more like a jerky than a tender steak. So we had a research goal to develop a novel meat analog, a whole muscle analog, which basically had to contain three things: a fiber structure, be extrusion-free, and 100% plant-based. Not only that, is we wanted to use existing proteins. We didn't want to find some novel protein and use this protein for the development of these products. We wanted to see what was already on the market. So we recently published a study earlier this year where we were able to take Zane protein. So this is a byproduct of corn manufacturing, and you can essentially mix this with water and dilute acetic acid, and you only raise it to about 40 degrees, and just through manual and repeated extension, you can create these viscoelastic kind of fibers. So what you can do is you can do this in the presence of a rapid swelling starch and a pea protein, and this acts as essentially a supporting network. So what we have here in figure B is kind of the final product. It looks kind of weird, but it much more closely resembles a raw kind of meat product. But we wanted to know what was actually happening. Why did this work? So that's when a synchrotron came into play. So we used FTIR-microspectroscopy to essentially look what was happening with the proteins. So we took a thin section of this product, and we put it at the beamline, and we identified essentially the interface between the starch network and the Zane protein. So once we had identified these regions, we did a k-means clustering to kind of separate the data. We noticed that the amide 1 peak in the FTIR spectra had a large shift from the starch region, which was about 6550, and then it converted to about 1642. So what that's meaning is that we had a change of alpha helix near the starch region, converting to beta sheets. And that, yeah, our zane is largely influenced by this supporting network that it's around. And we noticed that you can't just do this with any protein. It was specifically zane that gave us these properties. After that, we decided to chuck it into the computed tomography beamline at the CLS. So we wanted to see what was happening inside of the sample. So one thing that we are after is basically the structure of this fibers. So we're trying to represent the adipose tissue in a muscle, essentially. So what we were looking for were these long fibers within it. So what you see in the green, I'll kind of get this going again. What you see in the green is actually these zane fibers. Everything in blue is the starch, and red is the proteins. So we notice also that depending on the proteins that you use, you got a difference in basically what we call equivalent diameter, or the size of the protein globules in the network. So I'm just going to move on now to a second example, which is the plant-based dairy alternatives. So lots of these cheeses, these vegan and vegetarian cheeses on the market, something is kind of odd about them. If you look at the nutritional profile of these things, there's absolutely no protein in any of them. They all have, for your daily serving, they all have 0 grams of protein. If you look at like real cheeses, and I'm considering Kraft Singles a real cheese, even though I don't think it really is, but there's dairy in the product. But what do you know, it still has 3 grams of protein. Crackle Barrel, 7 grams of protein. So that's about 18 to 20% of the product is actually protein, where these plant-based alternatives have nothing. So yeah, where is the protein? We wanted to develop something that actually had some of the functional properties and also the same nutritional content, specifically the protein in these. So what we did first is there's 2 main things that you look for in a cheese, right? You want it to melt and you want it to stretch. So we did some of these tests. It's hard to see here, but this inner ring in the center, that's what it starts out as. And then you put it in a microwave for about 30 seconds and this is the result. Same thing with Crackle Barrel. You have amazing stretch, you have amazing melt. So if you look at these plant-based alternatives, do they melt? Absolutely not. It's just like a puck. They might get a little warm, they might get a little greasy, but anyone who's had these cheeses, they probably do it for a specific reason, like they're lactose intolerant or something. I mean, I've had them. The fiance's lactose intolerant, they're terrible. I hate them. So until there's something like better on the market, I'm not gonna probably eat them. And they also don't stretch at all. This middle one, I don't know, you could maybe say that that's a stretch. I think it's more just smashing it together and whatever comes out in the end, it's like a lucky pull, maybe, if you wanna call it that. So at this point, this is unpublished, so I'm just gonna refer to the proteins that we use as protein 1 and protein 2. So what we ended up doing is we used some of the existing methods to develop these cheeses, but we're finding a protein that could add the functionality that we wanted. So on the left side, we were able to use, basically get a 3 gram protein per serving, so the equivalent of those Kraft Singles. And we've seen that it actually melts reasonably well. But again, not all these proteins act the same. We use a different protein, and there's almost no meltability, and just the oil separates out. And do they stretch? Again, this one protein that we found stretches really well. So if Alejandro was here, he'd probably use the term, this is called food porn. I don't know if that's appropriate, but he basically insisted that I say that. And this one as well, it doesn't stretch whatsoever. So this is probably one of the reasons that the market doesn't usually use protein in it, is they don't necessarily add much to the product. It makes it more expensive, so why would you add it in? So yeah, we had actually found this, and we're quite satisfied with the results. Again, we wanted to know kind of what was happening. So we used synchrotron FTIR-microspectroscopy, and we identified in a thin section the starch, protein, and fat regions. And I should maybe take a step back. All cheeses are composed essentially of fat and protein and a little bit of starch. And all of the plant-based materials, you have to have the starch as like a supporting network for the protein and fat. So we actually found that the superior stretch and meltability one has actually a starch-dominated structure. So that's in red, and protein's in green, and the fat is in blue. And then we had actually found, again, these are all in the same ratios, that when you add this other protein, it kind of just mixes with the starches, but it appears to be more protein-dominated than the rest of them. And again, this is some ongoing research. This is all I can really talk about for now on this, but I can show you one cool image, and that is the structure of cheese. So if you take a CT scan of a regular cheese, there are these really small fat globules in the network, and they're all pretty spherical. So we noticed that when you melt the cheeses, they become elongated like the one on the right. So with the starch-dominated structure, you initially have these like nice spherical structures, and as they melt, they become elongated. The one on the right is that second protein, and it's already elongated in it, which kind of explains why it doesn't melt to begin with. If you've ever melted a cheese and then tried to remelt it, it kind of loses those properties after it melts once. And moving on to a little bit of my research, which I can go into a little bit more detail in, is chocolate. So for some reason, our lab loves comparing all food to concrete, and I'll do it again here. On the left side, we actually have a CT scan of a piece of concrete, and on the right side, a piece of chocolate. Chocolate basically is very similar in the sense where the cocoa solids and sugar act as kind of like these fine and coarse aggregates, and then it's bonded together with cocoa butter, which is composed of 3 main triacylglycerides or tags. That's the fats, the oil in chocolate. And if we actually take a look at this graph again, chocolate's the 5th largest contributor to greenhouse gas emissions. But unless we stop eating chocolate, there's not a total, like a lot of room for improvement. But even though that this area is small for processing, there's little that we can do. When you actually take a look at how much chocolate is produced and the energy in the tempering process, we might be able to fix that a little bit. So 20 kilograms of chocolate takes about 2.1 kilowatts of electricity. In 2020, 469 million kilograms of chocolate were produced. So that's about 492 million kilowatts of energy. So there is some improvement if we can reduce this tempering process to reduce the energy and environmental impact of chocolate. So if you don't know what tempering is, that's me tempering some chocolate by hand in the top right. It's essentially the process to direct the crystallization of the cocoa butter. So the cocoa butter crystallization or polymorphism is what's responsible for the text snap and the kind of gloss of a chocolate. Each of these polymorphisms have different mechanical properties and melting points, and we kind of refer to them as form 1 to 6. Most chocolatiers, when they're doing the tempering process, they're after form 5. That's the one that, again, it has a nice gloss snap. It melts in your mouth, not in your hand. And tempering essentially is heating it up past the crystallizer, past the melting point of forms 1 to 4, because they all sort of crash out at the same time. You heat it up, you melt all 1 to 4, and then you get a little bit of form 5 as a seed crystal, and then you let that recrystallize, and you do this a few times. And that's why it's so energy intensive, because you're continually heating and cooling the product under shear. So our research goal was, can we reduce this energy in the tempering process by basically directing the crystallization? So doing a little bit of background research, Aruda and Dimmick actually found that cocoa butter seed crystals, they have a higher proportion of something called a phospholipid. So these are what are called minor components. They're naturally in cocoa butter already, but usually removed in the refining process. But they found that phospholipids as amphiphilic molecules basically have a polar head group and a hydrophobic kind of tail group. They can play a role in self-assembly and could serve as basically a site to nucleate these tag crystals. So the group went through, just before I started with them, went through hundreds of these phospholipids. They just melted a chocolate, threw a bunch in, kind of see what came out on the other side. They found one, DMPC, that seemed to template chocolate really well. So on the left side is from a study we released in 2021 showing that the DMPC looks almost identical below a certain length scale in a CT scan compared to commercially tempered chocolate. So this was great, but when I came in, I was like, well, why does this work? So we had a place to start. We know that phospholipids are amphiphilic molecules. We know that basically based upon its polar head group and its tail length and volume, we can use something called the CPP, or critical packing parameter, to kind of guess what its shape will be. But not only that, is the environment that it's in, which chocolate is essentially just oil. We can also predict what structures will be produced. So we'll actually form these kind of inverse or reverse micelles. So what we want to do is make a model system. So we took a oil that's always liquid at room temperature, we added DMPC, a little bit of water, and then individual tags, and we're seeing if we could mimic what would be in a chocolate without all of the sugar and all the coca solids and everything else. So there's two requirements for micelles to form. One is a Kraft temperature. So that's the minimum temperature that's required to form an aggregate or a micelle, and the critical aggregation concentration. So the minimum concentration that it takes to form them. If you're below this concentration, you'll just have free-floating molecules in a solution. You don't actually have any aggregates. So we found that the original Chen study met both of these criteria. But something else was really interesting. In order to determine the critical aggregation concentration, we had to do something called interfacial surface tension measurements. So we basically just look at the interfacial surface tension between water and oil. And when you have just a neat oil, nothing in it, you have an interfacial surface tension of about 28 or 29. The POS, or the main tag in cocoa butter, the main fat in cocoa butter, it increases it, and that makes sense because it's a hydrophobic molecule, so it increases the hydrophobicity of this oil. When you add DMPC, being amphiphilic, it likes to aggregate around the water surface, so it reduces that interfacial surface tension. So what was happening next is when you have DMPC and POS, it further reduces it, showing that there's a stronger interaction between this fat molecule and DMPC than there is with the POS in the oil alone. And then when this happened, we got all of these things crashing out. These are essentially like macroscopic micelles. They're just giant kind of self-formed molecules. So we kind of had a hypothesis to go off of. So we assumed that the phospholipids were self-assembling into these reverse micelles. Previous studies have shown that DMPC specifically can form these sort of structures. So instead of DMPC being on the outside here, we thought that the tag crystals from the lamella of the cocoa butter were forming on the outside. So we took this to France. We did some small angle neutron scattering and some small angle X-ray scattering at the Canadian light source. So we confirmed that with small angle neutron scattering, we're having cylindrical structures being formed. And then again, this is all in the model system, and I'll get back to that in a minute. But when we did the small angle X-ray scattering at the CLS, we noticed that DMPC in oil, the oil itself, and the POS in oil, nothing happens. You can't even identify there's anything in the oil. They're the identical patterns you get. But the second that you add DMPC and POS, you get these two diffraction peaks here. And these are the 001 and 002 peaks of form 5 polymorphism of the cocoa butter. So this was really exciting. But we all know, like, well, what about a real system? Everyone can make a model system and come up with these conclusions. So we wanted to, again, test this in actual chocolate. So we redid micro CT at the Canadian light source and actually found that above a certain length scale where you're getting these macroscopic defects, these cracks essentially. And in the bottom left here, everything in the red is all the coca solids, everything in the green on this left one is air. On this right side, everything that's yellow and red is the coca solids and sugar, and everything that's green is the fat or the cocoa butter. So if we kind of zoom up on that, a properly tempered chocolate here on the left, there's no cracking. It's basically just a nice homogeneous piece of chocolate, and our DMPC chocolate on the right side is full of cracks. So even though it had the right mechanical properties, it was still having basically macroscopic defects, which we didn't want. This could induce bloom. If you have crack or lots of air pockets in it, you might increase bloom and things like that. So we took this a step further, and we looked at the fresh chocolate and added DMPC above and below this critical aggregation concentration. And in this graph here, the 001, 002, as I mentioned before, are the form 5 polymorphism in chocolate. This one at 45.2 is actually form 4. We don't want this in chocolate whatsoever. So if that's there, it's an indication that you have a poorly tempered chocolate and that something kind of went wrong. So we do notice that when DMPC is added above this critical aggregation concentration, you significantly reduce the form 5 or form 4 polymorphism, but not completely. We can look at this a step further, and we can do something called you can use the shear equation to calculate the crystallite size. And in the chocolate industry, they've been doing it for a while where they take one single peak, and they run this equation, and they say, yeah, this is the crystallite size. Well, when I did this, I kind of dug into it because if you have the same crystallite size and your beam broadening from your sample is only due to crystallite size, it should all show the same value. So if you see this downward trend, it means that you also have microstrain present in your sample. And vice versa, you can do a calculation for microstrain only, and if you see this decreasing trend as a function of 2 theta, you also have crystallite size effects. So when both crystallite size and microstrain are present, a Williamson Hall plot can be used to separate these broadening effects. So that's exactly what we did. And we actually found that even though that the DMPC in every other aspect appeared identical to regular chocolate, it actually had a giant crystallite size, even higher than recrystallized. So you can imagine a fresh chocolate that's tempered properly. As you're doing this, the shearing, you're breaking these crystallites smaller and smaller, and you actually have a smaller overall crystallite size. So with recrystallized chocolate is you're not only just getting rid of the form 4 in the tempering process, but you're also kind of letting the recrystallized crystals keep growing. And we had giant microstrain as well. So kind of how did all of this make sense? So essentially we have a reverse micelle, which is being formed, which is seeding the form 5 crystallization, but not completely retarding the form 4 growth. And this leads to essentially a very high crystallite size. And then a combination of the large crystallite size and self-assembled aggregates is giving really high microstrain and causes essentially microscale defects or leading to macroscale defects or cracking. So now what? So the hunt for a new phospholipid essentially began because we thought that there must be something else that works. So what we knew is that different phospholipids can promote or retard the tag crystal growth and nucleation at various temperatures. So this depends on the hydrophobic / hydrophilic interactions, the polar head size, etc. And we know that the large crystallite size and lattice inclusions can lead to high strain and microscale cracking. So our strategy moving forward is we just wanted a smaller lipid. But we know based on that critical packing parameter that using a smaller head would favor inverted micelles, but a smaller tail would basically favor a lamella structure and not promote any sort of micelle formation. So what we decided to do is we picked a very similar molecule with just a smaller head. And again, this is pretty new, so I'm not going to tell you which phospholipid we found because we haven't published it yet. But we did get some new data literally last week. So we used this new phospholipid, and I actually used handmade chocolate from scratch for this and also compared it to a 70%. So these are just brand new results. I put this together just this morning and threw this in here, and I thought I'd show you guys this. Left side, we have a commercial 70% chocolate. This is like a Lindt chocolate. This is the handmade recrystallized. So you see all these crackings, which we kind of expect from a recrystallized chocolate. And then our hand tempered, showing that, yes, I can make chocolate and I can temper it properly. And then the new phospholipid, so statically recrystallized, you just mix it in at about 0.1%, and then you have a perfectly tempered chocolate. So this was awesome. And then, again, we just collected this last week, is doing the exact same SAX analysis. So before we used a 90% dark chocolate, and this time we used a 70% chocolate. And what I was surprised to find is that the commercial chocolate, actually, if we zoom up on this section here, has a little bit of form 4 in it, which was kind of surprising to see. And if you compare that, the TA, or the tempered artesian, as I'm calling it, the handmade chocolate, it's almost identical to the Lindt chocolate. But the DMP, sorry, I almost gave it away there, no. Different molecule that we used. Basically tempers it better even than a commercial chocolate or hand tempering. So even though the hand tempered chocolate was really good, this other phospholipid is just perfect. There's no defects with it, 0 form 4. So what we did, obviously, is we wanted to do the Williamson Hall plot analysis again. And amazingly, is if you look at the crystallite size, very, very, very similar to the properly tempered, and almost no microstrain. And if you look at the recrystallized, it's just a giant crystal, 146 nanometers. So we're super happy with this, and hopefully publish soon, and then you can make your own chocolate. You don't have to pay an exorbitant amount for a fancy Lindt chocolate. So yeah, a couple of key takeaways from this is that food and agriculture accounts for a significant fraction of global greenhouse gas emissions. And there's definitely a need to overhaul the industry. I want to make a point that I'm not vegan or vegetarian, but I definitely understand the need to reduce the amount of meat that you consume. And I'm not going to stop eating it until there's something like okay on the market that, you know, maybe not indistinguishable, but doesn't kind of taste like crap. So I'm definitely all for this sort of research. And it's not for any sort of like vegan or save the animals reason. It's more for just an environmental standpoint. But I think that we can use synchrotron-based tools to kind of reverse engineer or guide the properties that we want to see in foods and then test those things there. And not only that, is we can use existing lower polluting plant-based materials in innovative new ways. So instead of looking for this brand new protein that no one's using before or developed yet, we can use existing things on the market and further explore their actual properties. And lastly, chocolate is freaking complicated. And I never thought going into this that chocolate would be this ridiculous. So with that being said, I just want to thank the Marangoni Lab, my advisory committee, a couple people from the CLS, and is it Lewis for swapping talks with me? I think so. Is it Lewis? Thank you for changing and making me actually talk in person and not online, so thank you. Yeah, thank you.